In this video we will discuss the electrostatic force between charge carriers, which is also called Coulomb force. And the Coulomb force is the basic mechanism for transporting energy into a circuit. And the force acts through the electric field, which we will also discuss in this video, and it propagates through a conductor. And the electrons within this conductor, some of them at least, they drift against the direction of this electric field, and then they transfer some of their kinetic energy to components in the circuit, which is caused by the Coulomb force. So let's discuss this very important concept to understand how energy is transported into your smartphone on which you might be watching this video. My name is Andreas from The Fearless Engineer, and here we go. In order to arrive at a mathematical equation which describes the Coulomb force, so we can compute the force between charged particles in space, we first need to understand the concept of electrostatic force between charged particles, and then we need to derive a definition for the electric field, which is a very basic concept that we will meet again many times, for example, when we get to the definition of the voltage in one of the next videos. So let's first discuss the electrostatic force. In order to construct a model for charge carrier movement in a conductive material, such as copper for example, we have not yet introduced in the video series you might have seen until now a source that really causes this movement. But before we talk about such sources, we first need to describe the force, the electrostatic force that acts between charged particles. In the 18th century, a very famous physicist called Coulomb, he conducted research and experiments on the force effect of charged bodies, which have been known for a very long time, dating back to the old Greeks. And he was the first to really arrive at a mathematical way to describe the amount of force depending on the charge of a certain body. And his definition, his equation, it included the electrostatic force F depending on the amount of charge Q and the relative distance R between two bodies. So in this small diagram here you can see a positively charged proton on the left and a negatively charged electron on the right in a distance R of each other, and there is a force vector pointing from the positive to the negative charge. Of course, there's also a force vector in the opposite direction, because if the forces are fixed in space, the forces will cancel each other out. So F will have a counterforce minus F pointing in the other direction. But what we want to do now, we want to find a way to compute the size, the strength of this force F acting on the negative charge emanating from the positive charge. In this video we want to keep things relatively simple, so we are only considering point charges. And Coulomb's law states that the potential of a point charge to exert force on other charges is uniformly distributed over an enclosing sphere. You can see the basic idea here. We have a sphere around a center charge, and we can easily compute the surface area of this sphere as 4 times pi times r squared. So if you place another charge anywhere on the surface of this enclosing sphere, the force acting on this charge will be identical for every position. It's evenly distributed over the entire area. And if you shrink the surface area and you place the same charge somewhere on the shrunken surface, the force it experiences will be stronger because the potential of the center charge to exert force is now spread over a smaller surface. So the larger the surface over which we have to spread the force effect, so to speak, the weaker the force on an individual charge placed somewhere on the area will be weaker. Which is why we get to a definition here, the definition of the electric field, which describes the effect of the charge, and we define it as the ratio between size, magnitude of the charge divided by the surface area of the enclosing sphere times the permeability of the material through which this force field propagates. In the case of vacuum, it's called E0, and it's this value here, which you can see down below, 8.8454 times 10 to the power of minus 12 coulombs per volt times meter. We have not yet discussed the concept of voltage, so bear with me on this one for a few more videos until we get to a sound definition. But this electric constant here is used to describe how the electric field of a charge permeates through the vacuum. So if you expand the sphere, and this essentially happens when you increase the radius, you will get a smaller field because it has to be evenly distributed, or the force effects of the center charge have to be evenly distributed over a large area. And if you shrink the sphere by making r smaller, you increase the strength of the electric field the closer you get to its center. Up until now, we have only discussed a single charge in space, and we have seen that a single charge causes an electric field to propagate through space, which may cause force effects if it encounters another charge somewhere. Now, if we place the charge q1 at the distance r from a second charge q2, we can calculate the force, the Coulomb force between these two charges, by using the electric field of the first charge at the location of the second charge. If you recall the enclosing sphere around the center charge is actually essentially q1, and then you place the charge q2 somewhere on the surface area of the enclosing sphere. That's exactly what we are doing here, and we are describing it by using this equation, which you can see here. So we have a force between two charges, F12, the Coulomb force between charge 1 and charge 2, and it's essentially the product of the amount, the magnitude of the second charge times the strength of the electric field of the first charge at the position of the second charge. And this problem is symmetrical because if you fix both charges in space, one will exert a force on the other, but the other charge, the second charge, will also exert a force on the first one. So we have two force vectors, one pointing from plus to minus and the other one pointing from minus to plus, for example. And this is why we can formulate this problem in a symmetrical way. We can either say Q2 times E1, or we can also say Q1 times E2. So we can also enclose the second charge in a sphere, basically causing this electric field E2, and then we can extend the sphere by increasing the radius R12 until it touches the first charge, and this is the same force which we will then arrive at as the force caused by the first charge. And if we now simply enter the equation for the electric field from the previous slide, we get this definition here, the force between two charges. So Q1 times Q2 divided by the surface area of the enclosing sphere surrounding the first charge times the permeability of the vacuum for the electric field. And in order to get a better understanding of how the electric field in space actually looks, you can look at the left example of these two here, and you can find a positive charge on the left and a negative charge on the right, and the electric field propagates from the positive to the negative charge on the right. And in case you have two positive charges, you can see that the field actually propagates away from these charges. All the vectors point outwards, and in between these two positive charges, the electric field vectors, they're actually opposing each other, with an area here in the middle where the electric field is basically almost cancelled out in case of a symmetrical problem with no other charges present. And by looking at these electric field vectors here for the two examples, you can easily see their effects on the Coulomb forces between the charged particles. And in case there's not only a single charge on the left and a single charge on the right, but we have instead several stationary positive and negative charges on a cluster on the left, a cluster on the right, we can find that the field in between is approximately homogeneous. So if you take a whole bunch of positive charge carriers on the right, on the left, and an equal number of negative charge carriers on the right, and if you position them in space, also using the simulation which I have used here to derive this electric field vector field again, you can see that the electric field vectors pointing from the positive side to the negative side are almost parallel. And if you place a non-stationary charge in the middle between these stationary charge clusters, you will find that there is a Coulomb force pushing this negative charge away from the cluster of negative charges, and there is a second Coulomb force which is pulling this negative charge towards the positive terminal. So a free charge in between these two clusters is both pushed and pulled at the same time, and the motion will be against the field direction from the negative charge cluster towards the positive charge cluster. And this is the basic principle of a battery or a power source in a circuit. If you expose a grid of copper atoms to an electric field, such as you can see here in the animation down below, you will find that the free electrons, the valence electrons, which are free to move in between the spaces between the atoms, this cloud of electrons begins to drift against the field direction. So there's a uniform motion of this entire cloud of electrons against the field direction. And the flow of electrons in a certain medium under the influence of the Coulomb force is what we call electric current. This is how electric current comes about. We have an electric field that permeates, for example, a copper cable. We expose the free electrons in this copper cable to the electric field, and the Coulomb force acting on these individual electrons then forces them and makes them move against the direction of the field. And we can calculate the strength of the Coulomb force by using the equations which we have derived in this video here. For now, that's all. I hope you enjoyed the video. If you have any questions, please do not hesitate to drop me a question down below in the comments. I wish you a nice day. See you next time here on The Fearless Engineer.